Hi, I'm John, and this is Alp, and today we're going to talk a little bit about some academic work that Veridise recently published in an academic conference called CAV, which stands for Computer-Aided Verification. And so essentially both of these papers are intended to, are at the intersection of ZK and formal methods, where they're intended to allow formal methods to better reason about and find bugs in ZK circuits. And so there are two papers that we published there because at Veridise we still have a lot of connections with the academic world, and we often collaborate with academics. So Alp was on a paper called
Multimod, and maybe I can talk a bit about it. So it's a work we did together with colleagues from Stanford. So basically the idea is some new method that help with the tooling for the automated detection and for security assessment. So basically what you do is you rephrase your security question that you want to have verified in terms of a logical statement, and then you just want to check that this logical statement is satisfiable, or maybe to show that it is not satisfiable. And so one difficulty there is that like microprocessors, they work, let's say, with bits, so arrays of bits. So you work basically modulo integers like 2 to the power 64, for instance, right? And then many modern ZK systems, they would work modulo a certain prime number. So you will have different moduli, and your system will have statements that are written in either one of those moduli. And then there are modern tools called SMT solvers that you want to employ, but they have a very hard time really dealing with reasonings in various moduli. Right? They do usually quite well when you work modulo prime, for instance, but if you also say, okay, but then I have also these statements modulo 2 to the 64, now combine this is where most solvers have problems. And our approach was to kind of have a system that can work with different moduli at the same time. So it has different parts that take care of the different moduli, so they can reason within their own moduli, but then there's a way of them to also exchange information. So you do some reasoning modulo, let's say the prime, you get some information out of it, you prove certain lemmas, for instance, and then you can transfer that information to the other units. So there's like a lifting and lowering methods that allows you to do that. And using that, we were able to kind of show that many problems that normal ZK applications had problems where the solver could not finish on time could be solved. Yeah. How about your paper?
The other paper that we published at CAV was Zequal, which was joint work performed by me, Shankara, who also works at Veridise and is our head of ZK security, and Ishal, who is a professor at UT Austin, but also the president of Veridise. And so basically what Zequal does is it kind of is intended to go beyond the automated verification of determinism in ZK circuits, and it is intended to actually verify more or a stronger property in ZK circuits. And so it kind of goes beyond that by looking at how traditional program verification works, where in traditional verification you have a program that needs to be verified, but then you also have the user specify some intended behavior, and this is performed as, or the user provides this information as a specification, where the specification says, this is the intended behavior of the program. And so in ZK circuits, the thing that Zequal kind of relies on is we already do kind of have a specification that's being provided by the user. And this is because the user is going to specify two different things when they create a ZK circuit. They're going to create this thing called a witness generator, which is a typical program which is going to take in inputs, but then it's going to generate what's called a witness, where a witness is just an assignment of variables to values. And so this witness is going to encode all of the variables which are then checked by the constraints. and the constraints just enforce some conjunctive formula. And so the witness generator is essentially going to perform some computation, and that computation is supposed to be then accepted by the constraints, where the constraints are essentially the ground truth, and they are what the ZK circuit is intended to check. And so the witness generator essentially provides us with a very good specification, because now the user has specified in this other form what the intended behavior is, and that's as a typical program. And then the constraints are what is supposed to accept any output that's generated by this witness generator. And so that means that we can now check the values that are computed in the witness generator against the values that are constrained within the constraints to say that, yes, the constraints over here are performing effectively the exact same computation as the witness generator over here. And so we basically formalize this notion of consistency, which says that your constraints are effectively performing the same computation as your witness generator. And it can do this in a way that is automated. So essentially, the verifier itself is going to take in the witness generator and the constraints, and then it's going to prove that the witness generator is effectively checking that the computation encoded by, or that is performed by your witness generator, is encoded within your constraints. And so in that way, you're able to not only prove determinism, because your witness generator has to be deterministic, but you're also, and it has to be deterministic because there is no source of non-determinism in any of the witness generators that we see. And so that's how we end up proving determinism, but you also now prove something stronger, because you're proving that a specific property holds, which is not encoded in when you're checking determinism, which is that it's also performing the same computation that's specified over here. And the reason why this is powerful is because, first of all, you can encode arbitrary computation as your witness generator. So it essentially lets you verify more arbitrary properties about your constraints. And then the other thing that is very interesting and very useful about it is we find that people who are writing ZK circuits have a much harder time writing constraints than they do writing the witness generator. And that's because constraints are essentially encoded as specific, specific conjunctive predicates that need to be checked. And so your predicate is going to say something like A times B equals C, and so on. And so they are much more restricted in their form, but also the programming of constraints is vastly different, where rather than actually performing computation where you say A equals B times C, you're now just essentially encoding everything as equalities that are being checked. And so the reason why this is helpful is because people are much better at writing the witness generator. And so by checking that your constraints are consistent with your witness generator, you're basically checking that this thing that people are not very good at writing is consistent with this thing that people are actually used to writing, because the witness generator is basically just a typical program.
And this flows directly into the tooling, I suppose.
Yes. So in both cases, these are things that help with the tooling. So with multimod, that's something that we, I think, already have implemented or are soon migrating into a verifier like Picus, because Picus uses the theory of finite fields, which I think is where this was implemented, right? In CVC5, right? Yep. And then Zequal is something that we're currently working on open sourcing as part of an Ethereum Foundation grant. So those are just some of the things that we've been working on recently at Veridise, because we want to keep working on advancing the security of the space. And yeah, there's much more that we have coming soon, but these were just things that we thought it would be useful to talk about and share.